In this demonstration, we'll walk through the tools required to isolate a pack of cylindrical batteries into individual cells, measure the step height of the cathode, and inspect the flatness on the top of each contact point of each cell. In this scenario, the customer needs to ensure a safe and secure contact of each battery cathode. Note that we'll be using a pack of simple AA batteries for today's example, as our EV battery inspection projects are proprietary and subject to NDA. Still, the principles and end goals remain the same. Scan settings, sensor position and exposure. Before we move to the measurement tools, note that we had to spend some time on the scan page settings to ensure we are acquiring good image data for measurements. This sample scan is acquired using a 2520 blue laser profile sensor. The two key adjustments we focused on were physical sensor position and exposure settings. First, we used the chamfer on the port edge of the G2520 to mount our sensor at the optimal angle to mitigate reflection off the curved metal surface of each battery. Second, we took time to adjust exposure for the right balance between acquiring detail and reducing reflection. If you're following along at home, we assume you're familiar with these settings, so we won't go into further detail. If this is your first time using the Gocator software, I recommend you sign up for the Gocator G2 Profile Sensor Fundamentals course on LMI3D.com before using this video as a tutorial. One last note before we move to applying measurement tools. We have purposefully flipped this battery pack between Scan 1 and Scan 2. This is so we can show you how to isolate single battery cells, as well as track the center point of each cell by anchoring measurement tools. Overcoming reflection points and noise. Now that we've acquired good surface scan data, the first step is to eliminate noise using the surface filter tool. Even after taking time to adjust the angle of the profile sensor and exposure levels to minimize reflection from the polished metal surfaces, we still find there are a few floating reflection points that our measurement tools might pick up and give us false measurements. Remember, please keep filters to a minimum so you don't accidentally alter your data points to a point of falsely representing your object. Let's go to the measure page and let's add the surface filter tool. In this example, we do not need to enable region because we are applying the filter to all battery cells. In the filter type drop-down menu, select median. Set level to low. The median filter smooths out each kernel of pixels, helping wrangle outlier data points, such as our floating reflection points, while still remaining true to the precise form of your object. Now, note that to be able to see the filtered image, you must go to the Data tab and select Filtered Surface. The final step for this tool is we will rename this filter tool to Median to keep your tools organized. Separating battery cells. The second measurement we'll put in place is the surface segmentation tool to separate the battery cells. Note that the tops of these AA batteries are about 14 millimeters in diameter. Add the surface segmentation tool. In the Stream drop-down menu, select Surface Filter Median. Do not enable region, as we want to capture all battery cells and use the surface segmentation tool to isolate each cell. In the part area minimum, input 140 millimeters squared, meaning we will ignore anything with an area of less than this. In the part area maximum, input 200 millimeters squared, meaning we will ignore anything with an area greater than this. Check the Accurate Measurements checkbox. Check the Show Details checkbox. In a perfect world, if the top of these batteries were completely flat and entirely in view of the sensor, the area would be about 196 millimeters squared, 14 by 14. However, due to occluded areas and edges, you can see the area of these are closer to about 149 millimeters on average. Going to frame 1, we note that 2 of the battery cells in the middle of the pack are touching, so the surface segmentation tool cannot distinguish them as 2 separate items. Use the part edge filter kern size to erode the edges and separate these. To see how the part edge kern size is affecting your scan data, navigate to the Data tab and turn on the Diagnostics surface. This is the area we were focusing on to separate the 2 battery cells. In the background filter kern size, input 5 points. This keeps the edge filtering low while separating the cells. In the background filter iterations, leave that as 3. In part edge filter kern size, input 5 points. In part edge filter threshold, input 3. In number of part outputs, input 5, as we are separating 5 battery cells. Let's navigate to the Measurement tab. In the Measurement tab, turn on X Center 1, Y Center 1, Width 1, and Length 1. We'll be using the X and Y center point of battery cell number 1 for future measurements. In the Features tab, turn on Center Point 1, 2, 3, 4, and 5. In the Data tab, turn on Surface 1, 2, 3, 4, and 5. Highlighting each surface, you can see how the cells are isolated in preparation for measurement. Finally, in the Ordering drop-down menu, select position Y increasing. For this example video, we will focus on cell number 1 at the top, so it makes sense to order the cells descending down the Y-axis, or top to bottom. Measuring step height of the cathode. Next in this example application, our customer needs to measure the step height between the top of the cathode and the main cylinder of the cell. To do this, we'll need to identify a bare part of the main cylinder to measure that's not wrapped in labeling or protective coating. To do this, let's add the Surface Mask tool. In the Stream drop-down menu, select Surface Segmentation Surface 1. In masking mode, we will leave this to include data in region. In the Mask Type drop-down menu, select Circle. Fit the region of interest to the bare part of the cylinder around the cathode. I recommend using 2D top-down view with intensity view on to make finding this easier. In inner diameter, input 7 millimeters to create a ring around the cathode. Navigate to the Anchoring tab. For X anchor center point, select Surface Segmentation X Center 1. For Y anchor point, select Surface Segmentation Y. Now that we've set this tool to anchor to the surface segmentation center point, the surface mask region of interest will track cell number 1 in any position. Navigate to the Data tab to see the extracted region that we've created. Rename this tool Surface Mask 1 Ring. Now that we've isolated a bare section of the battery cylinder to measure from, we can inspect the step height of each cell. To do this, we will be using a combination of surface plane, surface circular edge, surface position, and feature dimension tools. Add the surface plane tool. This will provide us with a reference plane for the feature dimension tool to use. In the Stream drop-down menu, select Surface Mask 1 Ring. Do not enable region as the extracted area from the Surface Mask 1 ring is already isolated. Navigate to the Features tab to view the plane output that we'll be using as the bottom reference of the step height feature. Rename this tool to Surface Plane 1. Next, let's add the Surface Circular Edge tool. We will use this to increase the accuracy of tracking the center of each battery cell. You may have noticed that the surface segmentation provides a center point for each segmented cell. However, it's not as accurate for two reasons. One, the entire cylinder is being calculated instead of just the cathode. And two, the circular edge tool allows us to be more precise with chosen data points. In the Stream drop-down menu, select Surface Segmentation, Surface 1. Move and adjust the region of interest box to capture only the cathode of the battery cell. In caliper count, input 30. In caliper length, input 1 mm. In caliper width, input 0.5 mm. Only data points inside the calipers will be calculated to form the circular edge. In the Edge Source drop-down menu, select Height. In the Step Direction drop-down menu, select Falling. In the Edge Search Direction drop-down menu, select Outward. In the Edge Selection Type drop-down menu, select Best. These settings adjust which data points will be selected within the calipers. In the Outlier fraction, input 3%. This will ignore the top and bottom 3% of outlying data points captured by the calipers. Navigate to the Anchoring tab. We will anchor the circular edge tool to the segmentation center point so that it will follow the single battery cell we are inspecting. In X, select Surface Segmentation X Center. In Y, select Surface Segmentation Y Center 1. Rename this tool to Surface Circular Edge 1. Next, let's add the Surface Position tool. Using the Surface Position tool, we can identify the center X, Y, and Z position of the cathode. In the Stream drop-down menu, select Surface Segmentation, Surface 1. Move and resize the region of interest box to include the center of the cathode. Keep in mind that the region of interest box must remain square for this tool, so keep the box to the main contact patch of the cathode. In the Feature drop-down menu, select Average. This calculates the average position of all data points inside the ROI box. In the Measurements panel, turn on the X, Y, and Z measurements. Navigate to the Anchoring tab. In the X, select Surface Circular Edge 1. In Y, select Surface Circular Edge 1Y. If you cannot find the surface circular edge Y in angle, make sure that you have turned this measurement on in surface circular edge. Now, let's look between frame 1 and 2 to ensure our anchor points track the battery cell number 1 the way we want it to. I'm happy with the way that tracks, so let's rename surface position to surface position 1. Add the feature dimension tool. The feature dimension tool, like the other feature tools, does not use a region of interest box. Instead, you must select your references from a drop-down menu. We will be using the previous tools we set up as references. In the Stream menu, select Surface Segmentation Surface 1. In the Point drop-down menu, select Surface Position 1 Point. This is the average point of the cathode contact area we set up in the last tool. In the Reference Feature drop-down menu, select Surface Plane 1 Plane. This is the plane calculated from the ring we took from the main cylinder of the battery cell. In the Measurements tab, turn on Height and Distance Measurements. The distance measurement accounts for diagonal distance as well. Rename this tool Step Height 1. Measuring the flatness of the cathode contact area. The final step is to measure the flatness of the cathode contact area, ensuring there are no burrs or high spots that could lead to an insecure connection. Add the Surface Flatness tool. In the Stream drop-down menu, select Surface Segmentation Surface 1. In the Region Type 1 drop-down menu, select Circle. Fit the region of interest to the main contact patch of the cathode. Don't worry about the rounded edges that curve away from the contact area. In the inner diameter, input 0, meaning we will calculate all data points inside the circle. In the Global Flatness Mode drop-down menu, select All Points. In the Data Filtering drop-down menu, select Local Percentile. Set the high percentile to 100%, so as to include all data points to the highest Z point of your region of interest. Set the low percentile to 10%, so as to exclude the lowest 10% of data points found in the region of interest. This will help ignore any of the curved down edges that we may have accidentally included. In the Measurements tab, turn on Local Flatness 1. Navigate to the Anchoring tab. In X, select Surface Circular Edge 1X. In Y, select Surface Circular Edge 1Y. Rename this tool to Surface Flatness 1 Center. Finally, please note that this walkthrough is a simplified application made to apply to as many situations as possible. Your application will undoubtedly have many more conditions. So please reach out to us at LMI Technologies to help you solve the specifics of your applications by contacting us at sales@lmi3d.com. Thank you for watching.